Okay, let's begin. So for today, I have two related topics, which are how to interact with GNU Radio using Python. We are going to be covering two different aspects. One of them is how to call a GNU Radio flow graph from Python. So we will see how a GNU Radio flow graph can be compiled to a Python script, and then how we can either call that Python script from the command line or directly from some Python code. And I will be demonstrating that using a Jupyter notebook. And that can be quite useful for any kind of task which is not easy to express as a flow graph. In the first session, I gave the example of a radio astronomy observation. Usually in an observation, you go through several steps. You need to calibrate the telescope by pointing at a calibrator source. You need to maybe point the antennas, change some frequencies. So you need to run through a series of commands. And the way you would typically do this is with some kind of scripting language, which can be Python. And oftentimes you observe multiple sources, so you could have a list of sources and then a for loop or something like that to iterate. That is quite difficult to express by using a standalone GNU Radio flow graph, because the flow graph just represents how information flows during runtime. But you can have a flow graph for the data capture and data processing, and then you can have a standalone Python script for everything else. So that's the first part for today. And the second part is how we can make custom GNU Radio blocks in Python. So GNU Radio comes with many different functionalities already been built in, and most of those are coded in C++ for performance. But if we have some idea or some need which is not included in the library, then there's something which is called an embedded Python block, which is a relatively easy way to program from scratch a block using Python. So that should be the second part for today. For the first part, the material is, let me see. So scripting, there is this scripting folder. And then there is this GRC flow graph, which I already have open. And this one I'm going to work with the final flow graph because it doesn't have much which is new for us. Let me briefly comment the things which are new. So the things which are new is this parameter block. We haven't used parameter blocks before. And a parameter is a way to inject into a flow graph an external value, which can come as a command line parameter when we run the flow graph as a Python script from the command line, or it can come as a function parameter when we call the flow graph from some Python code. So we will see how this works, but just for now, the message is we have been using variables and Qt-GUI entries so far to specify any data value that needs to change. In here, we will be using parameters. So for example, I have a parameter for the R frequency. In other example flow graphs, we had a Qt-GUI entry to be able to change this at runtime on the GUI, or we simply had a variable. But in here, anything I want to be able to change from Python or from the command line needs to be a parameter. So I have a parameter for the frequency. And let me walk through the flow graph because then it will be more clear what the other parameters are for. So I have this RTL-SDR source. I'm going to be using the RTL-SDR stick. The sample rate is 2.4 megahertz. So I'm sampling 2.4 megahertz worth of spectrum centered at whatever R frequency I have in this parameter. And then I have the gain fixed to 30 dBs because that's a reasonable gain, but we could also include a parameter here for changing the gain if we needed to. By the way these parameters interact with the rest of the flow graph is just like variables or Qt-GUI entries. There is this ID, which in this case is called frequency. And then when we want to use the value of the frequency, we type frequency, for example, here. The next thing I have is this is going to model some kind of observation. Of course, it's not going to be a radio astronomy observation because the only thing I have here is an RTL-SDR stick with a small antenna on my table. But the idea is that what you have here, you could tweak and use in a real observation with a real telescope. So we are observing for a certain duration, and the duration is specified by this parameter. In this case, duration is just 10 seconds by default. This is a default value, so later on we will be able to change it. And I'm using 10 seconds just to make this run quickly, but you could use anything which is appropriate in your case. And the way the duration is controlled is with this head block. So the number of items that the head block lets go through is the sample rate times duration, and we need to round because this is a floating point number, because the sample rate is a floating point number. So nothing new, and then what we do is we have this frequency translating FIR filter to select some portion of the spectrum, and the portion of the spectrum we are selecting comes given by this frequency translating frequency, which is this parameter here. So it's currently set to a default of 800 kilohertz, but later on we will change it. And then I'm using this shorthand notation to define an anti-alias low-pass filter. This was basically the same as in a previous tutorial. The decimation is fixed, so where's that? Decimation 12. So with a decimation of 12 and a sample rate of 2.4 megahertz, the sample rate that remains is 200 kilohertz. So basically here we have some kind of tunable receiver, which at the moment is tuned to 800 kilohertz, and the bandwidth it has is 200 kilohertz. The output of this receiver is going to a SIGMF sync, which I'll explain in a second. This is very similar to a file sync, but it will also save some metadata. So we will be using these metadata to keep track of what we are observing and also to visualize the data on some online platform, which is called IQ Engine. So for the time being, you can think of this as a file sync. We are writing raw IQ data to this file. And then in here, I have basically the same as in the spectral analysis tutorial, which we have used often. I have an FFT size of 2 to the power 16, which is 65,000 points. Stream to vector, which is always needed for the FFT. Then FFT, I have this Blackman window, complex to magnitude squared to obtain the power. Then I have the integrate block for a non-coherent integration, and the integration period or duration is 1 second. It is defined here, and we are computing the number of integrations like so. It is roughly 1 second, right? Because here I have this round. Then I'm multiplying by a constant. I think I haven't shown this before, so let me explain how this works. So the integrate block is going to add all 37 FFTs, or rather the magnitude squared of 37 consecutive FFTs. And then that is the result of integrate. So it's summing. If I change the number of integrations, let's say I make these 50, then the sum will be larger, simply because I'm summing more positive numbers. The way to normalize this is rather than doing a sum, to do a mean or average. And the way to do an average is to do a sum and then to divide by the number of summands. So that's what this multiply constant block is doing. And multiply constant does what it says. It multiplies the input by a constant value. But in whenever we are working with vectors, such as in this case, we have this NFFT, the constant here needs to be a vector. It needs to be a list of the same size as the vector. And in here, this is Python notation, so this isn't specific about GNU Radio. If I want to make a list of NFFT elements whose value is 1 divided by integrations for all of them, then I can use this notation in Python. And you can see the value is 1 divided by integrations, which is this 0.027, etc. And the length is 65,000 elements. So this is what we need. If we were to use just 1 divided by integrations, we would get some error here because this needs to be a vector. So, okay, this is just the normalization to have average power. And then we are writing the output to a file sync. This we have seen before. And we also have this vector sync. So I will come back to the vector sync later on. But for now, the only thing you need to know about it, it's just a way of storing data in RAM. So it doesn't write files to disk. It only stores data in RAM memory. And then the nice thing about this vector sync is that we can access the data from Python. So if we are running this flow graph from a Python script, then we can read this data from the same Python script when the flow graph finishes. So we will be using that to plot the spectrum on a Jupyter notebook. So, okay, now that we have an idea of what the flow graph does, the parameters are going to be quite natural. So we have the duration, 10 seconds by default, these 800 kilohertz, which is where we tune these 200 kilohertz slice of spectrum that we are recording to an IQ data file. And then we also have parameters for the IQ file and for the spectrum file. By default, I'm sending these to /dev/null, which if you're familiar with Linux or Unix, you know that anything that is written here just disappears. So this is like a null sync in GNU Radio. In fact, the reason this null sync is called null sync is probably because of this dev null. But anyhow, this is so that if we don't specify a spectrum file, for example, then spectrum will be not recorded anywhere. It will be thrown away. However, since we are using the sigmf sync, this def null doesn't work, and I will show why in a minute, because sigmf actually has two files. One is the data file, and the other one is the metadata file. So trying to do this trick of sending the output to def null doesn't work well with two files. I will show why in a second. So, okay, this is the flow graph. Any questions about it? Great. Then the thing I can do with any GNU Radio flow graph is to generate a Python script. Oftentimes we have been running the flow graph by clicking this execute the flow graph button, but the button left of it says generate the flow graph. And let me clear this for clarity. So if I click here on generate the flow graph, it says generating blah, 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 RTLSDR receiver flow graph.py. So it says it's generating a flow graph, a Python flow graph, because any flow graph you have in GNU Radio Companion can be generated as a Python flow graph, and also oftentimes as a C++ flow graph. You can go here in the flow graph options, and somewhere, yes, output language, you have Python, you have C++. So in general, you can always use Python and you will get a Python script. If you are only using blocks which are implemented in C++, then you can change this here and generate some C++ code. You will need to compile it to be able to run it, but the advantage of this is that it doesn't require Python. So if you're running on a very small embedded machine or something like that that doesn't have Python, generating C++ can be useful. generating Python isn't necessarily slower than generating C++ because the only thing this affects is the wrapper, the code that instantiates all the blocks and connects them together. Even if we select Python here, behind the scenes, everything or most of it is implemented in C++. So for example, this head block will be implemented in C++ and so on. And also worthy of mention here, I'm using no GUI as generate options because I don't have any GUI flow graphs and I want to be able to run this without a GUI. So you can think of being connected to a remote server by SSH and maybe you just have the command line. So that's what this no GUI is useful for. So, okay, we have the RTL-SDR receiver flowgraph.py. We can go here. And this is RTL-SDR receiver flowgraph.py. By the way, where does the name of this come from? It comes from this ID. So during these tutorials, I have been always choosing the same ID as the name of the GRC file. You can see that the GRC file is also called RTL-SDR receiver flowgraph, and that's the most convenient thing to do to avoid mistakes. So we have the Python script here, and we can run it with -h or -help to get some help about the usage. So you can see that this Python script really behaves as a command line script or application. And for each of the parameters we had on the flow graph, we get a command line option. So for example, we have this duration, and then it says set observation duration in seconds, default, etc. And that corresponds to the label we have chosen here. So in here, you can put anything which is descriptive because it will show up in the help here. So this is our Python script. Let's try running because I said with the IQ file output set to /dev/null by default, it will fail. So let me show you why it fails. And the reason it says can't open file, and this happens because you can see it here, it says I'm writing the SIGMF data to devnull.sigmf data because SIGMF uses two files. One is called .sigmf data, and this is the raw data file, and the format is the same as with the regular file sync. So you can open the SIGMF data file using Python in NumPy as we have done before. And then there is a SIGMF meta file with metadata, and this is a text file in JSON format. We will see how that looks like in a second. So the problem is when we have this SIGMF sync, then the file name is actually the stem for the file name, and then it appends the extensions .sigmf data and .sigmf meta. So the problem is /dev/null.sigmf data cannot be opened because I'm a regular user, and anyhow, writing to this file is a bad idea. So this trick doesn't work for the IQ file output. If you don't want the IQ file output, you could always disable this block, for example. But anyhow, so what I'm going to do is make a folder here in temp. So let's call tutorial 1, and then RTL-SDR receiver flow graph, IQ file output, temp tutorial 1, IQ file, for example. And let's review what this is going to do. So this is going to tune the RTL-SDR to 98 megahertz. It's going to tune the 200 kilohertz receiver to 800 kilohertz above it. So I'm tuned to 98.8 kilohertz. On that receiver, I know that I have a local FM radio station here. So that's the thing we will be recording to this IQ file. And then we also have this spectrum file, which is going to go to def null. And this by default will last 10 seconds. Let's make it shorter in order not to wait so much. So let's make it 3 seconds. And in this way, we can press enter and just let this run. So it has run for 3 seconds. And you can see in the log, it says generating the SIGMF meta, which is the metadata file, and writing the data to this SIGMF data. And we can check that this has happened. So if I go to, what's that, tutorial 1, you can see we have these two files, and one of them is large because it's the SIGMF data file, and the other one is very small. This 353 bytes is the SIGMF meta file. So we can see what this file contains. It's JSON, so if you're not familiar with JSON format, it's roughly based on JavaScript in the sense that you have this syntax with curly braces and these objects. So you can nest different data types, and you are free to create your own structures. And for Python and for other languages, there are libraries which read one of these, and they will read it as your native data structure. So in Python, this will be read as dictionaries and arrays. And you can also write back in JSON format. So this is what JSON is. SIGMF is a way to store usually radio frequency information, but it doesn't need to be radio frequency. So anything which is a time series of data that somehow resembles radio frequency because it has some particular sample rate and some quantized data can be stored in SIGMF. So the SIGMF standard defines basically what these things are, the metadata values that you can attach to your dataset. And in this case, this is the SIGMF sync minimal, which is the one that comes with GNU Radio by default. There is also a more featureful SIGMF sync in some out-of-tree module, which is called GR SIGMF. So this SIGMF minimal block just writes the minimal amount of metadata to produce a valid and useful SIGMF file. And the thing it has is the data type. So this means how the samples are stored. And in this case, it's complex because we are writing I and Q rather than real variables. This is float 32, so 32-bit floating point, little endian. And in this way, then we can basically know how to open this with NumPy or with C or anything else. The sample rate, so in this case, is 200 kilohertz. Where does this sample rate come from? It comes from this sample rate variable. So here I have specified sample rate divided by decimation because you need to remember that we are after this decimation. Then version 1.0.0, this is the version of the SIGMF standard. So if in the future SIGMF evolves and adds some additional metadata values, then they will increase the version number. The hardware, RTL-SDR, you could put anything here about your recording hardware, what kind of antenna you're using, what kind of SDR, etc. And this comes from this hardware info. The author, this is self-explanatory, and there is this author field here. And there's also a description, so you can type whatever you want here to be able to remember what you have recorded. So in this case, I have just tutorial recording. Then we have these captures, and this says sample start. So whatever information comes here applies to sample number 0. So that's the first sample in the file. And it says the frequency is 98.8 megahertz. So that's the way to remember the frequency we recorded at. And this comes from the center frequency, which for some reason it's a drop-down menu, although it shouldn't be. You can type anything you want here. And what I have typed is frequency plus frequency translating frequency, because the RTL-SDR is tuned to 98 megahertz, and then we have this 800 kilohertz offset. So we need to add both of them. There is something else which is useful on captures, but unfortunately this SIGMF minimal sync doesn't set, which is the date time or the timestamp for the observation. So in that way, you can remember when the observation was recorded. But anyhow, this is already useful as a SIGMF metadata, and then any application we have that supports SIGMF will know how to interpret this data by relying on the metadata to know, for example, the sample format and the sample rate. An example of application we can use is IQ Engine. So I'm showing this because it's an online application. It works in the web browser, so you can run it from any platform, no need to install anything. And you go in here to iqengine.org. There is this start browsing button because it has a library of recordings that many people have done and sent to this IQ Engine platform. But another feature it has is this local file pair or local directory. So you can open files on your machine and you can browse them with this IQ Engine. So I'm using local file pair, and in this file chooser, I'm selecting both SIGMF data and SIGMF meta. You need to choose the two files which go together. So we open this, and then what we can see is here is frequency, the horizontal axis. The vertical axis is time. And then we can see the waterfall. So this is power, signal power versus time and frequency. Something we can use is, where is that? Here, display RF frequency. So using this option, we can select between displaying the radio frequency. So in this case, 98.8 megahertz, or the baseband frequency, which has this at 0, and then we can see quite easily that the total bandwidth is 200 kilohertz. In this case, this is a very short recording, so I can see all the recording at once on the window. Here we can see 3 seconds, and my recording was 3 seconds. But if the recording was longer, and we will see that later on, you have these this thing which is like a mini map where you can scroll and select just some small part of the file to see at each time. Something else about IQ Engine and also about SIGMF is the ability to do annotations. So there is this add annotation button, and then in here you get some box which you can drag. And suppose here there is some signal of interest, maybe there is some RFI or some, I don't know, SETI candidate. Let's pretend here there is some strong RFI. So you can label this as strong RFI and hit enter to finish. And the thing that happens is that if you go here to the raw metadata, we have these annotations. And now we have this annotation which we have created up here. And it basically contains the time duration, so from which sample to which sample the annotation happens, and also the frequency range. And these annotations could be generated by any application and displayed by any other application. So We could have some automatic detection of candidates, whether they are RFI or SETI candidates. And then we could have that application populate this list of annotations. And when we open this SIGMF meta file with the annotations on one of these applications, such as IQ Engine, we will be able to see all of these annotations. So that's quite useful to process large volumes of data with unknown signals. It's the main context in which this was invented, and maybe you will find it useful. So, okay, this is IQ Engine. Any questions about what we have seen so far? Okay, then let's continue. So if I go back here, where I was here, we have seen how to run this Python script as a Python script from the command line, and how to set the options as command line parameters. But something else we can do is to call this GNU Radio flow graph as a Python function, or rather as a Python class. And we can do that from Python code. And the advantage of doing that is that if we are already using some Python script to do whatever, so for example, to control our telescope for the observation, then it's easier to call the GNU Radio flow graph as a Python class rather than having to go through the Python script as a command line application. And also we can access each of the blocks within the GNU Radio flow graph. And for example, something we can do is to retrieve the data stored in this vector sync. By running on the command line, we cannot really interact with this vector sync. But by running this from Python, we can interact with this vector sync. So to do that, I already have prepared this receiver controlled Jupyter notebook. And what I can do is run Jupyter notebook here. And it will show this receiver control. So this is already written. Let me walk you through all of it and explain how it works cell by cell. So in the first cell, we don't have anything very useful. We are setting matplotlib, importing some common Python libraries. And then this is the important part. So it says from RTLSDR receiver flow graph, import RTLSDR receiver flow graph. And then this is importing my flow graph as a Python class. So the way this works is if I come back here, here is my Jupyter notebook receiver control.ipynb. Here is my Python file, which is a Python module. And then if I open this Python file, for example, in Emacs, or I could use any text editor, you can see that this is a whole bunch of auto-generated code, but there is something which says class RTLSDR receiver flow graph, and this represents my flow graph. So in here we have Python code to basically to have all the variables and parameters, to instantiate all the blocks we had, and then to connect all the blocks. I showed a much more simple example on the first tutorial. We also have some getters and setters for parameters and variables in case we need to change some of these during runtime. And then finally, there is this main function. So this is what gets run when we run the Python file from the command line as a Python script. You can see this if name main, we run main, which basically instantiates the top block class, which is RTL receiver flow graph, and runs it. We are going to be something similar to this main function, but within this Jupyter notebook. So we are importing this RTLSDR receiver flow graph. These are some defaults for figures, so figure size and the background color, white. And let me run this. So here's an example of how to run the flow graph. We have RTL-SDR received flow graph. We can specify some of the parameters. So if I go back to the Python code here, you can see that this init method for the class, which is the thing we are calling, has duration equal 10, frequency translating frequency equal 800, etc. For each parameter we added as a block on GNU Radio Companion, we have an argument on this init method. So I'm just going to change duration and IQ file output. So let me go back here. And duration 3 seconds, IQ file output /temp/audio recording, for example. So by doing this, I am creating the flow graph as a Python object. Then I need to assign this flow graph to some variable. So this is just a name. It could be anything. FG stands for flow graph, but you can call it however you want. And you can also have multiple flow graphs at the same time on the same Python script. And in this case, we just do fg.run, which means run the flow graph until it finishes. So I run this cell, and then the flow graph is running. It will take 3 seconds, and since it prints out some information to the terminal, the information will also show here. The nice thing is that we have access to this vector sync block as a Python object. And for that to work, is important to set the ID of this vector sync. But to set the IDs, we need to go on view and then say show all block IDs, because by default, these are hidden, since commonly you don't need to change the IDs. So by default, GNU Radio will give some automatically generated IDs. For example, this RTL-SDR source is called RTL-SDR source 0, and then you can go to the Python code and see that there is actually something called RTL-SDR source 0. And if I had a second RTL-SDR source, you can imagine that it's going to be RTL-SDR source 1. If you need to change the ID because you need a reproducible ID that doesn't depend on whether you add or delete blocks to the flow graph or what GNU Radio decides to auto-generate your IDs, you can always change the automatically generated ID by an ID of your choosing. And in this case, I have changed this to Spectrum Vector Sync. And then what happens is on the Python code, there is somewhere, let me search. Here it is, Spectrum Vector Sync. So this vector sync, rather than be called vector sync 1 or 0 or something like that, is called Spectrum Vector Sync. So that's what IDs are for. If you are not doing Python coding, then probably you don't need to use IDs. You do need to use IDs, by the way, for variables and parameters. We have been using those all the time without realizing. But since those are used 100% of the times, GNU Radio Companion always shows the IDs for parameters and variables, but not for the other blocks. So that's what that show all IDs option is for. So we have access to the vector sync as a Python object. We can run this file, and this is flowgraph.spectrumvectorsync. And we can see that this is a Python object at some memory address. Okay. But then how we can do something with this Spectrum Vector Sync. And the way we can see how to interact with any blocks, or in particular with the vector sync using code, is I wanted this URL is to either go to the documentation Occasionally in the documentation, there is some coding example. So in this case, there is actually a quite complete coding example. So it says you can run your flow graph, and then you can access your vector sync. In this case, it's called my vector sync, and call this .data method, and this will retrieve the data. The other thing you can look, and in some cases it's necessary to look, is the source code. So in this case, the documentation is clear, but in other cases, if you're trying to do something more specific, it might not be explained in the documentation. So you can go to one of these header files, and you can see that there is some data method which can be used to retrieve the data. There is some reset method which can be used to clear the data, for example, and there is some tags method which can be used to retrieve something which is called tags, which we haven't seen in these tutorials, but they are a way to attach some information to particular samples. So let's say some signal begins at some point. So in the sample where that signal begins, you can attach a tag saying, here some signal begins, and this is its frequency or its type or whatever. But okay, with the vector sync, we can call this data method, and it will give us back a list of numbers, which is all the data that has come here. So this is a list of numbers. It's not so useful on its own. The way to make it into something more useful is to convert it to a NumPy array, and also to remember that we are writing vectors of 65,000 elements. So this vector sync is going to store all the elements concatenated as a long list, as in here. But then we can use this reshape method to convert that list into a matrix with however many rows are needed, and NFFT columns. NFFT is also a property in the flow graph. So here we are accessing the flow graph once more. It is this variable. So if we were to change the value of the variable on GNU Radio Companion, then everything will still work, because on our Python code, we are using this flow graph NFFT to get the size of the FFT. So we can run this, and the shape of the spectrum is 2 times 65,000 element matrix. So it has 2 rows. Why does it have 2 rows? The reason is we have recorded data for 3 seconds or observed for 3 seconds. And then we would expect to get 3 rows in the matrix, because each of the rows is one of these integrations, and the integration duration is 1 second. But what happens, I guess, is these 37 doesn't give exactly 1 second, but slightly above 1 second. So with 3 seconds of data, we only have data to complete 2 integrations and almost complete the 3rd integration. But by the time the flow graph finishes, the 3rd integration hasn't completed, and so it's absent from this vector sync. So that's the reason we only get 2. We could fix this in any way we wanted. And we can plot these. So something to remember is these are in linear units of power. So usually we want to plot in decibels when we have both weak and strong signals. And the way to convert to decibels is this 10 times the logarithm base 10. And here I'm plotting the 2 integrations, so spectrum 0, spectrum 1. One of them is in blue, the other one is in orange. You can see that they are very similar, because the signals which are present here, which are FM radio stations, don't change so frequently. So these are 2 different times spaced by 1 second, and the spectrum looks quite similar in both of them. So now we have seen how to retrieve data from the flow graph, in particular these vector sync data, but also any variable. The thing we need to do when we are done with this flow graph is to destroy or delete the flow graph, because while the flow graph exists, it has the RTL-SDR open, so it has access to the RTL-SDR. And if I try to use the RTL-SDR from anywhere else, so for example, let's record again here, then I will get an error. So it says USB claim interface error -6, failed to open RTL-SDR device. And this is because the RTL-SDR is busy. So the flow graph I have here is still running. It's not running because it has finished, but it's still existing. So it still has access to the RTL-SDR. And since this is a hardware device, only one application can have access to it at any given time. So we can run this delete flow graph to release access to the RTL-SDR, and then we can check that if we have any other application trying to use the RTL-SDR, we can use it. So this is how to run a GNU Radio flow graph from Python code. This is a Jupyter notebook because I find Jupyter quite useful to plot data and to code interactively, but this could also be a standalone Python script that you run on a server through SSH or whatever. Any questions so far? Okay, so what can this be good for? Here I have an example observation. By no means this is intended to be like a real radio astronomy observation, because it's just an RTL-SDR on my desk here. I don't have a telescope. But nevertheless, we are going to pretend we are using an observation by observing through certain sources. And in this case, the sources will be different frequencies, because that's one of the parameters we can change with the RTL-SDR. And you can imagine that if we were doing a real observation with a real telescope, rather than going through a list of frequencies, we could go through a list of objects on the sky, and we will still have some very similar code. We could also probably have some Python calls to control the antenna, for example, where to point it on the sky, maybe also to change gains or anything which is needed. And this depends very much on the telescope in question. When we will visit the Allen Telescope Array at the end of this month, you will see how observations are conducted there with a Python script, and you will see what particular Python calls are needed to point the antennas, change gain, select the frequency, etc. But here the important thing is the structure and how you can have something which resembles a list of things to be observed and a for loop to go through these frequencies. So what are we doing here? We have a list of frequencies to scan, 98 megahertz, 95.5, etc., etc. These are frequencies where I know that there are interesting signals at my location. And we will go through each of them to give you an idea of how the radio frequency spectrum looks like. That can be useful if you are doing any sort of radio frequency work, because you might have RFI, and knowing what kind of devices transmit on each frequency band can be useful to try to identify which RFI you are seeing. So we have the frequencies. For each frequency, we have a different center frequency for these 200 kilohertz receiver. So just as a reminder, we have a bandwidth of 2.4 megahertz. We are recording spectrum data for all the 2.4 megahertz, but then we are also only recording IQ data for 200 kilohertz, somewhere in this 2.4 megahertz window. And this somewhere is the thing we select here. So these I have chosen because in these particular locations, there are signals of interest in my location. We will see how this looks like. Duration 10 seconds. So we are going to dwell on each of these frequencies for 10 seconds. We are going to collect all our spectrum data into a Python dictionary. So this is an empty dictionary. And then we have this output directory for the IQ data, which will be stored as a SIGMF file. And here I'm using pathlib to create this observation directory if it doesn't exist. So we have this make dir, and it's okay if it already exists. And then for each frequency and frequency translating frequency, I print something to be sure that my observation is running. Then I generate the name of the IQ file. So on the name of the IQ file, I'm going to put the RF frequency to remember which is which, but the RF frequency will also end up on the SIGMF metadata. And then we do as before. We instantiate the RTL-SDR receiver flowgraph class. We run for this duration, set the frequency translating frequency, and set the path for the IQ output file. And the spectrum file is still going to def null because the way we will access the spectrum information is using the spectrum vector sync data, because it's just a small amount of data, so we can have it in RAM on the vector sync and we don't need to write a file for it. So this is the same as before. We are converting to a Python array and reshaping it as a matrix, and we are storing it on this Python dictionary, which is indexed by the RF frequency. And you need to make sure to delete the flow graph, because this is going to run for several iterations. And if you forget to delete the flow graph, then in the second iteration, this will try to open the RTL-SDR again, but it's already open because the first iteration flow graph hasn't been deleted. So you will get an error. That's the reason this delete flow graph. Okay, let's run it. And basically this will print receiving on this frequency, wait for 10 seconds, and then print something else. So I guess this will take about a minute to finish. So it's a good point for any questions or comments you might have.
For that, for example, the most recent one, what's the difference between choosing your frequency translating frequency to be minus 200 kilohertz versus just maybe increasing your center frequency by that amount and choosing a different frequency translating frequency?
So this frequency translating frequency is selecting where in the whole 2.4 megahertz band my 200 kilohertz worth of spectrum that goes to the SIGMF sync is selected. So that's the thing we are choosing. I guess this will become more clear when we see the spectrum for each of the observations, but I can already show it here. So with the 98 megahertz frequency, this is the spectrum we get. And we can see there are several FM radio stations. So one here, one there. And maybe these are also weaker FM radio stations. And I want to tune to this one. So this is about 200 kilohertz wide, and it's at 800 kilohertz with respect to the center. Here I don't have a frequency axis, a proper frequency axis, but below I will show a proper frequency axis. So that's the reason I'm choosing 800 here. In this one, I guess these are different FM radio stations. So at 95.8, because you need to add these two, there is another strong FM radio station. So in each case, I'm picking the most interesting signal from that 2.4 megahertz slice to record as IQ data. That's the reason we got this particular station in the IQ recording. So this FM radio station is just this FM radio station, and the rest were discarded. Here it's mainly for demonstration purposes, because you could as well record 2.4 megahertz of IQ data, so you could omit this frequency translating FIR filter and just connect directly, and then you wouldn't need any of these. But maybe the point I'm making is if you were to be using a real telescope, which can sample a very large bandwidth, maybe 1 gigahertz or 600 megahertz. I don't know, maybe you just want to select a much narrower slice on that spectrum. So that's what this frequency translating FIR filter is trying to emulate here.
Okay, thank you. So just to make sure, for the second one in your list there, if you had said 95.8 E6 up top and 0 on the bottom, that would make no difference to the observation.
Yeah, that's correct. Although in the spectrum, I would get things shifted a little bit, because the spectrum for this one, the center will be 95.5. So if I change it to 95.8, then everything will be shifted a little bit. And if there would be something here, maybe it's off the screen in the other case.
Thank you.
Okay, so I guess this has finished. We have everything. So receiving 1090, which was the last one, yes. And then what we have been doing is to write things to this spectrum data Python dictionary, so we can run this spectrum data, and we can see that this is a dictionary. So the keys on the dictionary are the center frequency, so 98, for example, 95.5, and then we have an array of, I guess, 9 entries for each of these, because we were recording for 10 seconds, but maybe the 10th integration didn't make it. So that's what we have. Not very useful in this shape. So what we can do is some plots. And here's some code to produce some nicer plots that you can basically copy and paste for your own uses. And it doesn't even need to be something GNU Radio. This is just about plotting any kind of spectrum data that you have as a matrix. So let's see how this plotting code works. So we have the sample rate, 2.4 megahertz. As I'm seeing this, I'm realizing we could also get this from the flow graph in the same way we were getting the number of FFT bins. Then I have this waterfall frequency reduce. I will explain what this is in a second. And what we do is for each element in our spectrum data dictionary, so for each frequency and data matrix, we are going to do a plot. So first we prepare the data. We need some frequency axis. So this is to show the correct frequencies on the frequency axis. And the way we do this is we use this FFT frec, which gives you the frequencies corresponding to each of the FFT bins, frequencies. So we need the FFT size, which in this case is data shape 1. And we also need the sampling period, which is the inverse of the sample rate. So this gives us the frequencies of each of the FFT bins in hertz, because this is in hertz, or rather sample rate is in hertz. This is seconds. We create a new plot with 2 subplots. And then for the waterfall plot, rather than plotting this matrix, because it has 65,000 columns, and 65,000 columns is a lot. We don't have 65,000 pixels on the screen. So when you call imshow to plot such a kind of matrix, then basically imshow does something to not to plot all of the columns because you don't have as many pixels. And usually that is just take some of the columns or interpolate the columns. So what can happen is if you have some signal which is narrowband, it appears in just one of the columns, you might not see it. We were seeing some similar things with Watutil last week. So a way to improve on this problem is to say, okay, what I'm going to do is to group the columns in groups of 64, for example, and then I will only get 1024 groups of columns. And within each group, I'm going to compute the maximum because I want to compute maximum power over each group of frequency bins. So this is what I'm doing here. By reshaping, I'm doing groups of columns, and then the maximum only applies on the last axis. So that's maximum per each group. So this is my waterfall, and now it's 9 times 1024 matrix, which is much more manageable as a plot. Then what we do is to convert to decibels, to plot in decibels. The extent basically sets you the time coordinates here, so time and frequency. And yeah, not much to see here. So the frequency comes from the center frequency and then plus minus half of the sample rate. And this is for the top half of the plot. For the bottom half, we have the spectrum. So for the spectrum, we are plotting the average spectrum. We could also plot the maximum spectrum, minimum spectrum, whatever we wanted. And then the frequency, as before, we have to add this frequency, which is the center frequency, 98 megahertz in this case. And then we have this frec axis, which was this FFT shift, and this 1e minus 6 to convert to megahertz. And this H space to make the two of them close together and labels. So this is the way we can get these kinds of plots. And in this case, these are FM radio stations. So as you know, around 100 megahertz, we have FM radio stations in many parts of the world. You can see maybe 4 of them. Also some RFI, so all these narrowband carriers are RFI. Probably something in my computer or anything near my RTL SDR. And then this particular station, which is at 800 kilohertz from the center, is the one we have recorded to the IQ data file. This is another example of FM radio station, so a different frequency. And then this one at 250 or 300, I guess. Was it 300? Yes, 300 is the one we have recorded to the IQ file. So this one, the strongest one. Then what else? 117.5. Here we no longer have FM radio stations. In this part of the spectrum, we have aircraft signals. So we have aircraft navigation signals, and we also have aircraft communication signals. So between the pilots and the control tower, they will speak on amplitude modulation radio. It's still analog voice, and you can listen to air traffic if with the RTL SDR stick you have. If you go to this frequency range, you might see some airplanes talking to ATC, which is how the control tower is called. But in this case, the signal is here. We will see it better in spectrum. This is a VOR station, which is some aircraft navigation radio station. What else? 400 megahertz. Here in Europe, we have something which is called TETRA, which means terrestrial trunk radio. So this is the walkie-talkies that police, fire stations, maybe ambulances, all of them have. So basically public services, walkie-talkies and radios on police cars and such. In the United States, there is something similar, which is called P25. So it's a different system, but it uses the same frequency range. And here we have one of these signals. And if we scan across the band, maybe we can see some other signals. Going up more, 800 megahertz. This is LTE, so LTE is 4G telephone signals. Anywhere between 700 megahertz up to 900, and then in other parts of the spectrum, there are telephone signals. Mobile telephones are one of the larger spectrum users, as you can imagine, because these days, mostly everyone has a mobile phone and they want fast internet access on their mobile phone. So all of that uses a fair amount of spectrum. So in this case, we have two LTE signals here and there, and they are 10 megahertz wide, so they go off the screen. And this other thing here is called narrowband IoT, which is for Internet of Things. It's based on LTE, but it's much narrower, so that's the reason we can receive it completely with the RTL-SDR. Another example of telephone signals, 935 megahertz. This is GSM. It's the old telephone protocol. And finally, something quite interesting is 1090 megahertz. This is called ADS-B. This is a beacon that most airplanes have that continuously, or better said, periodically transmits the location of the airplane. So if you have gone on the internet or on an app on the phone where you can see a real-time map of aircraft, this is where the data comes from, this ADS-B data, and you can also receive it and decode it with the RTL-SDR. And it's also a nice signal, and maybe annoying RFI signal if you are trying to do something around this frequency, because it's often present. In most part of the world, you have aircraft overflying you, and it's a pulsed signal. So there are pulses, and so the way that this behaves as an RFI is quite different from a continuous signal, such as one of these. So, okay, besides these plots, I also got from the observation the IQ captures, and we can see all of them here. So I want to take a closer look at two of them. One is this 117.5, which is the aircraft navigation signal. And you can see it here. So it's a center carrier. And then there is this sideband, which is where the bearing information is encoded. So this will tell you where you should point your aircraft if you want to go to this radio beacon. That's basically how these work. And these also send an identification using Morse code, but it sends it maybe every 1 minute. So in 10 seconds, we didn't get it. This is what I was mentioning as the minimap before. So here you have the representation of the whole recording. Here there isn't much difference because the signal doesn't change so much over time, but you have these to scroll and select parts of your recording. So this is one of the example recordings, and the other one is this 1090 ADS-B. And you can see all the short pulses. So for example, here there seems to be a stronger pulse by the looks of this. And something else you can see is time. So something you can do is to toggle some time cursors, and then if you go here on time, I'm not quite sure how this works, but anyhow, you can see that these are short pulses, so 1, 2, 3, 4, etc. Maybe within each of these there are multiple pulses as well. No, this is just a pulse. It's basically the frequency offset, the thing which looks like a complex exponential. So this is how the information is transmitted by sending pulses, which you can see here. Okay, so this was the first part for today. Any questions? So for the second part of today, I'm going to use where is it? Python blocks folder. There is here something which says Python block demo. And the flow graph I have opened here is almost the Python block demo, but it's missing the Python block. So here we have things we have seen before. And I want to begin by motivating this with another kind of fake observation that tries to mimic how a real world radio astronomy observation would look like. So let's say I just want to measure power using my RTL-SDR. Power across the whole band it receives, which in this case is 2.4 megahertz. So I want to use this for power measurement. And the reason why I might want to measure power is because in many cases, radio astronomy sources are broadband. So they emit radio frequency noise about over a very wide frequency spectrum, certainly much wider than 2.4 megahertz. So if I had my RTL-SDR plugged into a real telescope, then if I were to point the telescope antenna to some radio frequency source, I would just see the noise floor go up uniformly when I'm pointing towards the source, and then when I point away from the source, I would see the noise floor come down. And by measuring the difference between these on pointing or on scan and the off pointing or off scan, I can basically measure the flux of the source. So this is the kind of observation from radio astronomy I have in mind. So let's say I want to do that with my RTL-SDR, and I could do that in a very simple way by using the RTL-SDR source, and then I could do complex to magnitude squared. That would give me power, and then I can use the integrate block to integrate for as many samples as I want. This will set my integration time, and here we go. That's my power measurement. But I want to do it in a more sophisticated way by using the FFT, because first we also want to plot the spectrum. So if we want to plot the spectrum, we need to compute an FFT. And then because oftentimes calibration is done separately in each frequency bin. So that's one reason one could want to introduce an FFT, or also, and this is what I'm going to be presenting as the use case for this Python block, we could want to do interference cancellation on the frequency domain. And for that, we need an FFT. So rather than simply summing samples, what I'm going to do is to compute the spectrum. This is again nothing new. It's the same as before. And then I'm going to add all the frequency bins to get the total power over all the frequency range. So let's see how this works. This is the RTL-SDR source. It's tuned to 433.9 megahertz, and I've chosen that frequency for a reason. I will tell you why in a moment. And then I have 4,096 points. It's a reasonable size for just displaying a spectrum. We do the FFT, we do this 30 millisecond integration, I guess. And this could depend on the kind of measurement you're trying to do, but it will be useful for the interference cancellation we are going to use. And also for displaying things in real time. So we have this integration, which amounts to 18 FFTs or 18 summations. And then we have logarithm base 10 and the trick with repeat to display it on a vector sync. Probably we do not need the repeat trick here with these 30 milliseconds integrations, but anyhow, it doesn't hurt. And then, as I said, I want to compute the total power. So to do that, I need to take each of those 4096 element vectors, sorry. So each of these 4096 element vectors, I need to sum all of those 4096 elements, and that's one of my power measurements. And I will get one power measurement every 30 milliseconds. So how to sum all the elements in a vector? There isn't actually a block that does that, but we can achieve the same using blocks which do exist. So what we do is to use the vector to stream, which converts from vectors of size NFFT to vectors of size 1. This will basically forget that my stream is vectors. It will just say, okay, it's just a stream of samples. And they have, then I have these integrate blocks. So I'm summing 4096 elements. And then what happens is this is summing 4096 consecutive elements, which happen to be each of my vectors. So that's how I can achieve to sum up each of the vectors. And at this point, I don't have vectors anymore because of this trick, but also because I have summed each vector as a single number. And I can convert to decibels and use the repeat trick. And for this, I'm using a time sink. So I will display how power changes over time. And this is the sample rate. So it's the number of measurements per second, 32.5. But the thing I wanted to mention is the number of points. So the number of points is basically 1 second. So this is the number of points I have in roughly 1 second multiplied by 10. And the reason I'm multiplying by this 10 is because I have this repeat by 10. And I guess here, to be fair, I should also multiply this by 10 to take into account the repetition factor. So this should be 300 whatever. Okay, so this is how the flow graph works. What I'm going to show you is why I have chosen this particular frequency, and I'm going to show it in GQRX because it has a nicer spectrum display than GNU Radio. And you can see two things. One is that we have lots of narrowband RFI, but we also have these signals here. So the reason I have chosen this particular frequency is because it has some amount of RFI. This frequency in Europe is used for any kind of low power, short range devices. So think of car keys, remote garage door openers, those kinds of things. So, and also weather stations. So if you have one of those outside weather stations with an outside thermometer, it can also transmit here. So that's the reason I have a bunch of things here. I don't know what each of them are, but in here they are going to play the role of RFI. They are actually RFI if I want to measure power across this whole band. So if we run this flow graph, then what we can see is the same as in GQRX. And I have here my power measurement. And it's changing a little bit, but what I want to show is hopefully a strong RFI will come. Yeah, and you saw it there. So whenever we have some strong RFI that pops up for a fraction of a second, we get some large peak here on the power measurement. That one was huge. So that's the reason I have chosen this example. We have something where for some amount of the time we can more or less measure the power of the noise floor accurately, but occasionally there is strong RFI and that completely validates our data. So that motivates the practical example, with which I want to show how a Python block can be implemented. Because in this case, you can see that even though the RFI happens at different frequencies and it happens fairly randomly, it's always narrowband. So it only occupies a small portion of my frequency band. If I could select what parts of the spectrum are occupied by RFI by doing a power measurement and saying anything which has large power should be RFI. So let's not count that. Then I could do a better frequency measurement that would work as some RFI cancellation technique. It's a pretty basic RFI cancellation technique, but it's something simple enough that I can code it live, and it's also something useful enough for this case. So you will see the difference. That's what we are going to do. We are going to implement a Python block that does RFI cancellation by looking at each of the FT bins, and whenever they are large, it will replace the contents of that particular bin by 0. So it will remove all the power that is there. The way to decide what to cancel and what to leave without changes is by using the median. The median is very useful in statistics and signal analysis, because when you have outliers, if you are using the mean, the outliers affect the mean. If you have a very large signal and you are computing the mean, the very large signal will modify the mean. However, the median is not affected very much by outliers, because it's the value that leaves 50% of the FFT bins below and 50% of the FFT bins above. So if some of the FFT bins suddenly become very large, the median is not going to be very affected by that. So basically, we are going to be taking each of our FFTs. We are going to compute the median of these, how many? 4,096 points. And then we are going to have a threshold, and everything which is larger than the threshold times the median will be replaced by 0. So that's how our Python block is going to work. There isn't any block in GNU Radio which does that. It's a rather specific algorithm for this rather specific situation. So that's the reason we are going to implement the Python block. Any questions about the setup? Okay, so let's get going. The Python code itself is very simple. You'll see it's just 2 lines of NumPy. But the nice thing about it is that it illustrates how a Python block works. So if you are doing something more complicated, then it's not really a GNU Radio problem. It's a problem of how to do things in Python. So if you search for Python, there is Python block. There is also Python module and Python snippet. But here we are going to use Python block. And you get a block which is called embedded Python block. And by default, it has an example parameter. And if you double click, there is code. So we can write some Python code. And there is opening editor, which will open the system default editor or choose editor, which will let you choose from a list of editors that are installed in the operating system, this text editor, and this will depend on your system. So in my case, I can open in editor, and this is Emacs because this is the thing I have set up. Let me make this somewhat larger. So for example, like this. And the next thing is you get some template with a lot of explanations about how everything works. So you see it says each time this file is saved, GRC will instantiate the first class it finds, blah, blah, blah. So basically the way this works is you can keep editing this file, and whenever you save, the flow graph automatically updates with your latest version of the Python code. And then we have a class, and this class represents our block. So in this case, it's a sync block. There are other types of blocks, and occasionally you might need those, but the sync block is the most basic. It means synchronous, so sync means synchronous, and that means for every input sample that comes into the block, we get an output sample. And in our case, let me close this. The input samples are going to be vectors, so they are going to be these FFT vectors coming out of the integrate, and the output are going to be FFT vectors. We are just going to replace some of the FFT bins by 0. So this is an example of a sync block, because for every FFT vector we put in, we get a new FFT vector out. So sync block. We have init, which is the class constructor. And to this init method, we pass the parameters. So the parameters are these parameters that show here. And in this case, the parameter is going to be the threshold. I think we need to give it a default value, or at least it's recommended to give it a default value. So let's make it 10, for example. And then it says arguments to this function will show up as parameters in GRC. So I can save my file. So this is save. And you can see there is example parameter. I don't know why this hasn't saved as threshold. It will probably do later on. So let's keep changing things. There is a name, so this is the name of the block. It will show up in GRC. And I'm going to call this block RFI cancellation. Here it says if an attribute with the same name as a parameter is found, a callback is registered. Properties work too. The callback is the thing that lets me update the value of whatever parameter. So in this case, it will be the threshold at runtime. So while the flow graph is running, we are going to use this. And basically the notation is self dot whatever equals whatever. For each parameter you want to be able to change at runtime, in this case threshold, you need to include self.threshold equals threshold. So this is my block, and okay, now it has understood that the name is RFI cancellation and that there is some parameter named threshold. And I want you to notice that threshold is underlined. This means that threshold can be changed at runtime, because I have done this thing here with a callback. Something else we need to define is the input type and the output type, because if you notice here, it's blue, so that means complex. And this is no coincidence. It's because here the data type, we have complex 64. Complex 64 in NumPy is the same as complex float 32 in SIGMF or in other places. So it's 64-bit complex numbers, because the real and imaginary part, each of them are 32-bit floating point numbers. So what I want is float 32 here. And then I get these floating point input and outputs, but they aren't vectors. They are just single numbers. To get vectors, there is a special notation. And the notation that needs to be used is like this. So you put parentheses for a tuple, and then indicate the number of elements in the vector. Unfortunately, this needs to be fixed, so you cannot have a parameter and then use the parameter here. That would be useful, but I think it doesn't work, or at least it didn't used to work. But in this case, we have the FFT size fixed to 4096, and we could even do it like so if we don't want to repeat ourselves. So that is fine using a variable which is defined there. What we cannot do is to use one of these. So here we have 4096 element vectors, and in fact we can see that the connection can be done, and the arrow is black. So this is how the init method works. So this is how the properties of the block and connections are defined. Then the math, the operations that the block does, are defined in this work function. And in the template, there is an example which says multiply with constant. And it already shows the basic syntax for all of these. So the input samples come in these input items. The output elements go into these output items. And these are lists. And the reason these are lists is because the block could have multiple input ports or multiple output ports. In this case, it's just going to have one input port, one output port, but it could have multiple. So input item 0 is a chunk of samples from the first input port, and then output item 0 is a chunk of samples from the first output port. This works with chunks of samples. So what's going to happen is that every time that the work function is called, GNU Radio is giving our block a vector of elements. And I know in this case we have 4096 element vectors, but what I mean here is it will give us multiple of these vectors in general. So for example, it could give us 100 of these 4096 element vectors at the same time. And the reason it does that is for performance. Rather than calling work for one sample at a time, it calls work for a multiple for a large number of samples in general. And then we can use NumPy, for example, to operate on those samples, and that's more performant than calling work for each individual sample. So that's what happens. In our case, input item 0 is going to be a vector of or a list, or actually a NumPy array. That's the most appropriate term. It's going to be a NumPy array containing some FFTs, maybe 1, maybe 2, maybe 100 of them. And then the output, which is going to be the same format. So if this was 100 4096 FFTs, this is also going to be, how many did I say? 100 4096 elements FFTs. And the output needs to be overwritten here. So that's one way to do it. Here, the example is multiplication by some constant, but we want to do something different. So we will change the code. And finally, something else we need to take into account is this return. So this return returns how many items we have processed. In general, we will process all the items that we are given. So we return the length of output items, which is the same as the length of input items. This could say as well length of input items. It doesn't make a difference. But in some very specific situations, it depends on the kind of block you are implementing. Maybe you cannot process all the input at this given time because you need to wait for something or whatever. So in that case, you need to return the actual number of items you have processed, and the items you haven't processed will be available on the next work call. So that's how this works. In this case, let me check something real quick because I don't remember. And when you don't remember something, a good way to do it in Python is to print. So if I want to remember myself, what is print input item 0.shape, this will tell me what is the shape of the NumPy array, because I don't remember if these are already reshaped as matrices as we have done before. So let's try to run it like so. And with this, we are simply assigning the input to the output, which is something we want to do. Basically, we are going to do this and then set to 0 any bins containing RFI. And this is to do. So we will do this in a second. For now, let's check the shape of the input items. So to run this, we need to include this as part of the flow graph. And basically what I'm going to do is to replicate what I have here because I want to do a comparison. So I want to compare how things work before and after the RFI cancellation. So number of inputs 2, connect, number of inputs 2, and then connect. And let me see, yes. So basically on the first of these, I have without RFI cancellation, and on the second of each of these, I have with RFI cancellation. So I run these and I get a segmentation fault. That's confusing. Return code -11 is segmentation fault. So let me run this again just in case it was, yeah, it was something strange. Okay, so here in the terminal, I get my prints. So this is the shape. Remember, I'm printing input items 0.shape. So it's a matrix with 1 row and 4096 columns. What's happening here is that since the data rate is relatively low, my work function gets called for each of the integrations. But if the data rate was higher because I was doing shorter integrations, so maybe I can even show that if I put a 1 here. And then something you need to be aware is this window is not very efficient, printing lots of things. So if you want to plot lots of things, it's better to do it on a real terminal. So I'm going to go to scripting, not scripting, but rather Python blocks. And then I have my Python block demo start. I think that's the name. Yes, Python block demo start. Yes, and in this case, since I'm doing shorter integrations, basically I'm only integrating one FFT. You can see that each time the work function is called with a different number of FFTs because basically GNU Radio decides at runtime how to call things depending on how much data there is left to process and so on. It might supply more or less data to your work function. So whatever you implement needs to be able to deal with this situation. So, okay, let's put this back to integrations 18. And then what I'm going to do here is I have copied my input to the output, and I want to set to 0 any bins containing RFI. So what I'm going to do is a for loop. So for j in range input items 0.shape.0. This is the number of rows in my matrix. So in this example, it will be 1 all the time, but if we are running with a shorter integration rate, it might be 9 in one call and 4 in another, etc. So that's the reason we need a for loop. And then we want to calculate the median. So the median is np.median in NumPy. And then input items 0. You always need this 0 because it's the first input port of the block. The block could have several input ports. And then this is NumPy. So this whole thing is a NumPy matrix. So if I do this j or this, it's the same. This is the jth row. So I'm taking a row of the matrix. This is one of my FFT integrations, and I'm computing the median. Then what is RFI? It's everything which is larger than the median multiplied by the threshold. So I'm still using this thing, and then whatever points that are larger than the threshold. Remember, here you need to use self threshold because the threshold value has been stored into this self threshold inside the class. So any parameter you have, you will typically store it somewhere in self.something. So don't remember to use self dot whatever, self.median. So these are, let's say, R5 bins. These are the bins which contain R5. And then what I want to do is output item 0 j. Remember, we are always operating with the jth integration. And the R5 bins, we set it to 0. And this is our whole RFI cancellation algorithm. So it's something very simple, but it illustrates how some signal processing idea, something you want to code, it's easy to include as part of a GNU Radio flow graph. And then you can use GNU Radio to interface it with an SDR, for example, or to generate your signals or to do whatever. So have I removed my print? No. So let me comment this printout. And then the thing I'm missing is I want an entry for the threshold because I want to change this at runtime. So threshold. This is a floating point number. By default is 10. And here I have threshold. So now we can run this. And in blue, we have the original data. In red, we have the data after the RFI block. And what you can see is there are these RFI CW carriers, which are present all the time. And I can even make the threshold smaller. So if I make the threshold very small, so for example, 1, then this will start cutting away a lot of useful information, but this threshold parameter is kind of situation specific, so you can set it to wherever it basically keeps all the noise floor and cancels everything else. And the thing you can see is occasionally some RFI pops up. It only pops up in blue, so it's rejected by this RFI Python block. And then, oh, I couldn't stop that. So next time it happens, I'll stop. So here in blue is the power measurement without RFI. And in red is the power measurement with RFI. So you can see that whenever we have one of these short transmissions, which contributes to the total power without the RFI cancellation algorithm, with the RFI cancellation algorithm, the power measurement doesn't change by much. So here is what I couldn't stop in time. But you get the idea. So here are RFI bursts, which are brief in time, and also sparse in frequency. So they only occupy a small number of frequencies. And by doing this simple filtering, we can cancel this out. And this is a very basic cancellation algorithm. If you do any kind of radio interferometry analysis and you are using CASA, for example, there are RFI cancellation routines which are more complex than this algorithm, but they are based on the same kind of ideas. So any questions about this? Great. This is pretty much what I had for today. So with what we have covered, I wanted to give you a few examples of how by coding some Python, you can leverage GNU Radio and construct useful things. But by no means it's a full tutorial of what can be done, because you have all the power of GNU Radio and all the power of Python at your disposal. Nevertheless, it's a good starting point. So if you have something where you could use Python coding in GNU Radio, you can use these examples as a starting point, probably. So that's all for today. Next